computer system, there are two ways to make more powerful computation. The first one is called scale up, that we leverage hardware power inside a single machine. We use more powerful, for example, processor in replace the old ones. We use other we use high volume memory and so on. Another approach to do efficient computation is scale out. That is, we use multiple nodes to increase the available computing power. Just showing in this figure. Okay, with more powerful processor, more powerful hardware, or more node, it is not an easy task to use all the resources available, such as the scientist from Google, Jeff Dean, says machine learning, and in particular, deep learning, is an attractive alternative for architects to explore. Hence, machine learning experts and computer architects must work together to design the computing system. Only in this way, we can deliver the computing power needed by machine learning applications. Recently, David Patterson and others published a paper. In this paper, they also called for computer scientists or application developers to rethink the architecture of the computer system architecture. Their paper is named "A New Golden Age in Computer Architecture." They say how to support machine learning applications with architecture-specific optimization. Here, the work I share here is on how to support efficient DNA training on Jinlei type-light supercomputer. Okay, this is the background. Before we go into the details of how we do, I'd like to show you some challenge to do efficient DNA training on supercomputer. First, let us examine the organization of type-light supercomputer. For type-light, the basic unit is Jinlei medical processor. Then each processors are assembled in one computing node, and 4 computing nodes comprise a computer plug-in. 8 plug-ins consist of 1 supernode. For the whole supercomputer, there are 660 supernodes. So these computers, these computing nodes filled in 40 racks. In each rack, there are 1,024 chips. That is a medical processor. For each processor, there are 4 core groups. In each group, we have 65 cores. Okay. On top of the core group, we use process to do computation. On the computing core of each chip, we use the thread model to do computation. Okay. Yeah, this is the detailed architecture of the many core. In each core, there are 4 core groups. In each group, there are 1 management processing unit, that is MPE, and 64 computing processing elements. The 64 CPE are organized in an array. There are 8 CPEs in a row, and there are 8 CPEs in a column. CPEs in the same row or same column can do communication directly. This is here, we will show row communication network. If the CPE in different row and different column want communication, they must do the communication via the transfer network with the help of transfer agent. Okay. The challenge to build a DNA training framework, at least here, we need to redesign a variety of basic DNA layers according to the process architecture. We need to do efficient parallel training to use the register communication and to avoid the imbalance during processing. Also, we need to think disk I/O so that we can load data from the disk as fast as possible. Okay, let's examine how to do the concrete optimization. To us, there are 4 principles. The first principle is to fully utilize the 8x8 CPE mesh for computation intensive tasks, just as shown in this figure. To make full use of the resources, we should do parallel in 3 levels. In the instruct level, we need to use the 2 pipeline of the instruct loading. In the middle layer, we should do data parallel with 1 CPE. That is, we use 1 instruction to process multiple data. On the upper layer, we should do task parallel among different CPEs. Principle 2, it is about disk I/O. We should always use LDM, the local direct memory, as the intermediate cache for data movements between DDR memory. This figure shows why we should do so. Theoretically, the bandwidth of memory is about 32 gigabytes per second. If we send the data from memory to cache directly, the measured bandwidth is only about 9.9 gigabytes. However, as we use LDM, the measured bandwidth is about 28 gigabytes. So the gap between them is huge. Principle 3, we should increase available memory bandwidth by transferring large data blocks. As shown in the figure, if we use different granularity of the data, different throughput can be throughput or bandwidth